Today I am going to discuss how rate of a chemical reaction depends on temperature. For most of the chemical reaction, rate increases with increase in temperature. It has been experimentally observed that for a chemical reaction with rise in temperature by 10 degree, the rate or rate constant of the reaction nearly double. So for a chemical reaction with a rise in temperature by 10 degree, the rate constant or rate of reaction is nearly double. It has been experimentally observed. So how rate of a chemical reaction depends on temperature? It was explained by Arrhenius with the help of an equation, and that equation is known as Arrhenius equation. So Arrhenius equation is k in equal to a into e to the power minus ea divided by r into t. So this is the Arrhenius equation. It is the Arrhenius equation in exponential form. This is the Arrhenius equation in exponential form. So in this equation where k is the rate constant, k is the rate constant for a chemical reaction. Capital A, it is a constant. It is known as Arrhenius constant, also known as frequency factor, also known as pre-exponential factor. So small e exponent here, small e represents here exponent. Ea, it is known as activation energy. Activation energy, it is the energy gained by the reactant molecule before producing the product in a chemical reaction. So before producing the product, reactant molecules must be attain certain minimum amount of energy, which is known as activation energy. So details about the activation energy we will discuss in our next video. So R here, R is ideal gas constant or universal gas constant, and capital T here, temperature. Capital T is the temperature in Kelvin scale. So capital T is the temperature in Kelvin scale. So Arrhenius, how rate of a chemical reaction depends on temperature, it was explained by Arrhenius with the help of this equation. So this equation is known as Arrhenius equation. This is the Arrhenius equation in the exponential form. So in this equation, k is the rate constant, a is the Arrhenius constant, or it is also known as frequency factor, also known as pre-exponential factor. So Ea, it is a very important term. It is a very important factor related to a chemical reaction, which is known as activation energy. So regarding activation energy, we will discuss in our next video. So R, it is called ideal gas constant. T is the temperature in Kelvin scale. Now taking natural logarithm of both side of equation 1. Equation 1 means this is Arrhenius equation. Let us consider it is an equation 1. Now taking natural logarithm both side. So natural logarithm ln equal to 2.303 log. So ln k equal to ln a into e to the power minus EA divided by R into T. So this is similar to log A into B. So log A into B equal to log A plus log V e to the power minus EA divided by RT. Then ln K equal to ln A. So this is similar to log A to the power B. So log A to the power B equal to B log A. So plus minus EA divided by R into T ln E. So ln K equal to ln A plus into minus, this is minus EA divided by R into T. So ln E, this is equal to 1, just like log 10 equal to 1. Similarly ln E also equal to 1. So this is the Arrhenius equation in the natural logarithmic form. This is the Arrhenius equation in the natural logarithmic form. Now we can convert this equation into logarithmic form. So ln equal to 2.303 log K. Similar this ln 2.303 log A. So minus EA divided by R into T. Now dividing the both side by 2.303 से बोथ साइड इक्वेशन का बोथ साइड डिवाइड कर देने से देन इसको 2.303 से डिवाइड कर देने से log k रह जाएगा. इसको 2.303 डिवाइड करने से log a रहेगा और इसको डिवाइड करने से फाइनली वी हैव 2.303 RT. So this is also one of the Arrhenius equation in the logarithmic form. So when we plot a graph from this equation log k, we are plotting a graph log k against the 1 by t. Here 1 by t term also, here 1 by t, then 1 by t. Then we have this type of graph. So intercept of this graph, intercept means इनको extend कर देने से जिस point में intercept होगा, that is called intercept of this graph equal to log a. That means from the value of intercept we can find out the value of Arrhenius constant or Arrhenius factor a, and slope of the graph equal to minus EA divided by 2.303 R into T. That means from the value of slope we can find out Arrhenius, we can find out activation energy for a chemical reaction at a particular temperature. So this is the graphical representation of this equation. In this graph log k is plotting against the 1 by t, then intercept of this graph equal to log a. That means from the intercept we can find out the value of Arrhenius factor a, and from the value of slope we can find out activation energy for a particular reaction. Now let us consider at two different let us consider at two different temperatures T1 and T2, rate constants are K1 and K2. Now applying the Arrhenius equation at these two different temperature, log K1, because at temperature T1 rate constant is K1 equal to log A minus EA divided by 2.303 R into T1. Let us consider this is equation number 2. Similarly, at the temperature T2, let us consider rate constant is K2. So log K2 equal to log A minus EA divided by 2.303 R into T2. Let us consider this is equation number 3. That means for a chemical reaction at the two different temperatures T1 and T2, हम लोग क्या अप्लाई किया, Arrhenius equation अप्लाई कर रहा है for a chemical reaction at the two different temperatures. When temperature changes, rate constant also changes. At the temperature T1 for a particular reaction, rate constant is K1. At temperature T2, rate constant is K2. It has been experimentally observed that if temperature increases by 10 degree, then rate constant will increase by 2 times. It has been experimentally observed. Now equation 3 is divided by equation 3 minus 2. हम लोग सब्सट्रैक्ट कर रहा है इक्वेशन 3 से इक्वेशन 2. देन log K2 इक्वल टू log K1. देन माइनस कर देने से क्या होगा, log A कैंसिल हो जाएगा. देन माइनस EA डिवाइडेड बाय 2.303 RT2. again minus EA divided by 2.303 R into T1. So this is log A minus log B. So log A by B. Now this is minus EA divided by 2.303 R into T2, or this minus plus EA divided by 2.303 R into T1. So log K2 by K1 इक्वल टू, सपोज हम लोग पॉजिटिव टर्म को आगे कर दिया, नेगेटिव को पीछे कर दिया. सो EA डिवाइडेड बाय 2.303 R into T1 माइनस EA डिवाइडेड बाय 2.303 R into T2. Now EA divided by 2.303, this is we can take common EA divided by 2.303 R, then 1 by T1 minus 1 by T2. So log K2 by K1 equal to then EA divided by 2.303 R. T1 and T2 is taking LCM, then T2 minus T1. So this is also an Arrhenius equation to determine the activation energy EA for a particular reaction at the two different temperatures T1 and T2. So in the next video we will discuss how we can calculate activation energy for a particular reaction at a particular temperature, and we can also calculate the activation energy for a particular reaction at the two different temperatures T1 and T2. In the next video we will discuss about the activation energy, and we will solve different types of numericals related to calculation of activation energy. So thank you.